Hello, I'm going to present our work on WALT, Watch and Learn 2D amodal representation using time-lapse imagery. This paper is a joint effort between myself, Dinesh, Robert, and Srinivas at Carnegie Mellon. The goal of the paper is to learn amodal representation, that is, detecting and segmenting both the visible and the occluded regions of an object. This representation will help in tracking, reconstruction, and other downstream tasks in busy scenes. One possibility is to use human annotations to train these representations, but human annotators perform poorly in occluded regions, as can be seen from the disagreement between multiple annotators. This disagreement increases with increase in occlusion percentage. We observe this across different representations, that is bounding box and instance segmentation. And human annotations for amodal learning in current datasets like Coco and Kitty are very limited. Thus, we cannot learn all the occlusion configurations over different object categories. On the other hand, multiple large synthetic datasets have been proposed to tackle the occlusion problem. Such datasets can be used to learn amodal representation for virtual environments, but do not translate well to real data due to domain gap. In this work, we present the best of both the real and synthetic worlds for automatic occlusion supervision using a large readily available source of data, time-lapse imagery. We automatically mine unoccluded objects from the time-lapse imagery that can be composited back in a realistic way to provide large-scale supervision for training. In the time-lapse stream, detecting unoccluded objects is distinctly an easier problem to solve compared to annotating or distinguishing objects under severe occlusions. Given detections of each object in the image, we compute the intersection between the bottom of each bounding box with other bounding boxes. Assuming objects lie on a plane, unoccluded objects are detected using a threshold on the overlapping region. This way, we automatically detect a large number of unoccluded objects. Any of your favorite pre-trained detectors or segmentation networks can be used here. We used scarce, which had accuracy of 90% and 75% AP for unoccluded vehicle and people respectively. We show results of unoccluded object detection over a time-lapse video. Observe that our method is able to find unoccluded objects even in busy intersections. Being patient pays off here. Over time, our method discovers tens of thousands of unoccluded objects at diverse positions, orientations, and appearances. These mined unoccluded objects can be composited back into the scene in the following way. We compute the background images for each hour of day from the time-lapse data. Then, unoccluded objects are composited in layers back into the background image. We call the resulting dataset as clipart WALT or Seaworld. Diverse objects are composited back into the image in various configurations, setting the stage to learn amodal representation automatically. Here are examples of compositing for a variety scenes like boardwalk, traffic intersections, sidewalks, and beaches. These Seaworld generated images and ground truth occlusion configurations are passed through a network to learn amodal representation. Given an image and the ground truth from compositing, every bounding box contains three components: the object that needs to be segmented, the occluder, and the occluded. Disentangling these three objects per bounding box improves the amodal representation. We illustrate the pipeline to learn these three layers. First, similar to scarce, we pass the ROI feature from HRNet backbone to the occluder network, and then the occluded network. Combining these two representations, we pass the added features through a amodal segmentation network. We compute loss for amodal segmentation and bounding box for each of the layers individually, using the ground truth occlusion configurations from Seaworld. We compare our method to other networks trained with the same datasets. Observe that our method is able to perform better than previous proposed methods with increasing occlusion percentage. Here are some segmentation results on people walking on a boardwalk. Observe the accurate amodal segmentation of people even under severe occlusions. The prediction are computed per frame and no temporal smoothing was used. Here are segmentations of vehicles with large occlusions. We observe that learning robust amodal representation automatically improves tracking of severely occluded objects. We have collected a large time-lapse dataset of 100 cameras captured across the world. We have released data from 20 cameras captured by us. For additional results, code, and dataset, please visit our website walt.cs.cmu.edu. Thank you.